Okay, ladies and gentlemen, good afternoon. Let's continue with our course in heat and mass transfer. We are making use of the textbook of Cengel and Ghajar. We are busy with chapter 11 on heat exchangers. On this chapter, we've looked at different types of heat exchangers, and we have looked at the different resistance methods of the different resistance terms. It is all about the fact that at any specific wall, if we've got a heat exchanger, if this is one fluid and that is another fluid, there's heat transfer occurring. There's the heat transfer rate. In this case, from the hotter fluid, of course, to the colder one. What is important is the heat transfer coefficient on this inner wall and the heat transfer coefficient of that wall. So what the heat transfer coefficient is there is not going to matter. It's only where the heat transfer occurs. And in general, we can write the resistance term as equal to 1 divided by the overall heat transfer coefficient. U is the overall heat transfer coefficient. And as you'll be able to see from this equation, it actually puts together the heat transfer coefficient on the inside, the heat transfer coefficient on the outside, as well as the fouling that can occur on the inside and the outside, and the resistance term, the thermal conductivity resistance. So RFI will always be the fouling there, and RF0 would be the fouling there. Yesterday we've looked at that, and it was given to us that the heat transfer coefficient on the inside was 800. That was the RF value, 0.0004. The heat transfer coefficient on the outside was 1,200, and there's the heat transfer the fouling factor also on the outside, 0.0001. Yesterday we did the substitution, and I've showed you in this case that it is sort of a balanced problem. There's not one specific term which is the dominant one, and there are not many terms which are very small. I think this one was 5%. Okay, so the total resistance was equal to R equal 0.00532. From this we can solve U multiplied by A, which is 399. What is important is that the overall heat transfer coefficient is not equal to that of the outside. Why? Because the areas are different. If the areas are the same, then the overall heat transfer coefficient on the inside, or based on the inside or on the outside, would be the same. Very important concept, and let's continue it a little bit further and look at the heat transfer rate. So if we now want to calculate the heat transfer rate for this problem, then it is important that we look at what happens with the temperature as a function of X, because we need a temperature difference. And I always draw the sketch, and I would recommend that you also do that. That is typically the inlet temperature there of 80, the outlet temperature of 60. Okay, over the total length of the heat exchanger. Okay, where the temperature is 60, the inlet temperature is 10. So if you put 10 there, and the outlet temperature of 50, 50 should be approximately there, then that is in principle what is happening. Okay. So with that temperature distribution, we can calculate the LMTD. And in heat exchangers, I've discussed it to you at the beginning of this lecture, what is different from this chapter than other chapters. Typically the chapter that you did on internal forced convection, where you could have a wall with a constant heat flux or a wall with a constant wall temperature, is that in this case you've got two different streams separated by the wall. Okay. And the general guideline is you can always use LMTD, except if you're going to end up in the situation where that temperature and that temperature is the same, then this is not going to work. You'll not be able to calculate the LMTD, but then you can just take that temperature as the temperature difference. Okay. So LMTD means it is this temperature difference. That temperature difference is 30. 80 minus 50 is 30, minus this temperature difference, which is 50. 30 minus 50 divided by the ln out of 30 divided by 50, those two. You might worry about the fact that you're going to get a negative sign here. You can just ignore it, make it a positive sign. It will still work. It is very robust. And then you will get LMTD of 60.15 degrees Celsius. Okay, do you agree? It's easy, huh? Okay. Yes? Did somebody want to say something? You are frowning.
Why is the temperature difference larger?
Good. Okay, I've done it on purpose, so that obviously can't be. If you look at 50 and 30 there, if you've done that, you must tell yourself, I expect the LMTD to be between 30 and 50. It cannot be 60. Very easy to make a calculation error. So if you go and do it, it is 39.15 degrees Celsius. Okay. Right, now we can calculate the heat transfer rate very easily. Heat transfer rate Q is equal to UA multiplied by LMTD. Okay. And now you can ask, but which ones should I use? Should I use inside or should I use outside? That is why I've showed you this. The product is always the same. This value and that value might differ, but then it will be because the areas differ. So there's the UA, which is 399, multiplied by the temperature difference, which is 39.15. And I think that's about 16 kilowatts, something like that. Okay. Am I right? Okay. Now, not all heat exchangers are the two types that we've started with, the counterflow or the parallel flow. The counterflow and the parallel flow are very easy. With the parallel flow one, the inlet temperature is going to be on this side and the outlet temperature is going to be on that side. However, now we can start having very complicated heat exchangers, cross-flow heat exchangers, etc. And the question is, what do we do with other types of heat exchangers? Okay. Well, like we do in engineering or in the sciences, in many cases, when we do not really know how to handle these theoretically very sound and correct, we use a Jippo factor F, which is a correction factor. However, the correction factor is always based on the fact that you use the LMTD as if it is a counterflow heat exchanger. We're going to do examples and I'm going to show you exactly what I mean with that. So F is the correction factor. And typical correction factors for different types of heat exchangers is given in table 11.19 in your textbook. Let me show you some of that. Okay, so there you can see some correction factors F. There's the correction factor, and it now looks complicated because suddenly there are other things here. There's an R term, so there's the R, and you can ask, but no, I don't follow what is going on here. Well, it is actually very easy because all the information is given here. So there's, for example, how you calculate P, and there is how you calculate R. So you'll see these correction factors are all a function of R. There's the different values of R, and there is P. Okay. However, to calculate the P and the R, we need the temperatures, and you'll see here schematically, this is typically a common shell and tube heat exchanger, so it has one shell, and there's the temperature going into the tube, and there it is going out. So the small t's is used for the fluid stream on the inside. And there, with the capital T's, we can see how it looks, the inlet fluid there and the outlet fluid. So if you just make sure that the capital T's and the small t's are aligned, then you'll be able to correctly calculate P and R and then the correction factor. We're going to do an example like that. So what you will see is normally that F is smaller or equal to 1. Okay. And F is equal to 1 for counterflow heat exchanger. For counterflow heat exchanger, it's equal to 1. And it gives typically the value of P, T2 minus T1, divided by T1 minus small t1, and R is equal to T1 minus T2 and T2 minus T1. So, and in the sketch that we've typically looked at, schematically, that was T1 and that was T2, and typically like that, and that is T1 and that is T2. Okay, so it looks very easy until you get into the exam. Then suddenly you're going to ask a question, because most probably I'm going to give you a problem where there's a phase change in one of these. Okay, and then when you start doing the calculations, then you say, ooh, suddenly things are going wrong here, because now my R goes to infinite. Okay, when can that happen? When that two temperatures are the same. And that temperatures are the same, it means it can be a condensing fluid or a boiling one. Then R is infinite, and it doesn't show on the graph. If you look at that, you can't get a value. Well, in the fine print again, F is equal to 1 for phase change. Very, very important. So the moment you've got a phase change, which is evaporation, boiling, condensation, etc., then F is equal to 1. Okay, let's do two examples. We're going to start with it very simple, and then we're going to make it more complicated. So in this example, we've got a heat exchanger. I'm going to draw it like this in terms of geometry. Something like that. And here we've got steam at 30 degrees Celsius. And here we've got water at 14 degrees Celsius going in and going out at 22 degrees Celsius. That's water. And it is given to us that the surface area for heat transfer is 45 square meters, and the overall heat transfer coefficient is equal to 2,100 watts per meter Kelvin, and this is a thin tube. Okay. So you can be very privileged if you get a problem like this in a test and an exam. Obviously in industry, this is typically what you're going to get, but most probably in the exam, it will also be part of the problem that you must get U. Okay. To get that, you will have to get the mass flow rates, Reynolds numbers, go through the equations, get the heat transfer coefficients, the inside and the outside, go through the whole thing, take into consideration fouling if there's fouling, and then get to the value of this. So you will also see that the overall heat transfer coefficient, it's not given on either on the inside or the outside. Why? Although this is a circular tube, they say it is a thin tube. And if it's thin, if it's very thin, then the area on the inside and the area on the outside would be approximately be the same. And if they are the same, then the heat transfer coefficient based on the inside area and the heat transfer coefficient based on the outside area would be the same. Okay. Students also have a problem with this. If they look at this, they say in the exams that, oh, I forgot to give the outlet temperature. This is again something that you need to understand. If you look at the TS diagram, okay, if you've got steam at 30 degrees Celsius, okay, then that is saturated vapor, saturated fluid, and that would be 30 degrees. If the inner temperature of the steam is 30, then the outlet temperature will also be 30, except if more information is given, such as it is subcooled with 10 degrees or 5 degrees or something like that. But no information like that has been given. It therefore means that you now know that that temperature is equal to 30. So if you go and draw the temperature as a function of X curve, you have to make of this a counterflow heat exchanger. It is not a counterflow heat exchanger, it's a cross-flow type of heat exchanger. You can just look at the two directions of the fluids. But you have to draw it as if it is a counterflow. Draw as if a counterflow. This is very important. So let's start on the hot side. On the hot side is 30, in and out. And let me choose it like that, it doesn't matter. So that would be the hot side. Condensation, okay? Then we've got counterflow. Take note, inlet temperature is 14, okay? And outlet temperature is 22. There is 22, so therefore, something like that. Okay. So, therefore, we can now say the LMTD as if this heat exchanger is a counterflow heat exchanger, okay, is equal to 30 minus 22 is 8, minus 30 minus 14 is 16. The lim of the two terms, the temperature difference is 11.15. If we look at this, makes sort of sense, isn't it? It should be between 8 and 16. It's in between, so it looks okay. Right, now we can go and calculate the heat transfer rate by saying it is equal to UA multiplied by the correction factor, because it is not a counterflow heat exchanger, multiplied by the LMTD as if it is a counterflow heat exchanger. But F should be equal to 1. Why? Because we have condensation on the hot side. Therefore, calculating the heat transfer rate Q is equal to U, which is 2,100, multiplied by the surface area is 45. The correction factor F is equal to 1, multiplied by the LMTD is 11.5, and that would give us an answer of 1,087 kilowatts. Another typical, so there is that. Another typical question can be, determine for us the mass flow rate of the steam and the mass flow rate of the water. Okay, let's do that also. That is now very easy because we have the heat transfer rates. Okay, so for the steam side, the heat transfer rate is equal to the mass flow rate multiplied by the change in enthalpy for the steam. The heat transfer rate is equal to 1087 multiplied by 10 to the 3. It's equal to the mass flow rate of the water multiplied by 2431 multiplied by 10 to the 3. And it gives the mass flow rate as equal to 0.45 kilograms per second. Mass flow rate of the steam, 0.45 kilograms per second. Similarly for the water, however, we cannot now say it is equal to the mass flow rate multiplied by the change in enthalpy, because it's not a phase change fluid. It is a single phase fluid, so it is equal to m dot Cp multiplied by the outlet temperature minus the inlet temperature. The heat transfer rate is 1087 multiplied by 10 to the 3. It's equal to the mass flow rate which we require. Cp value is equal to 4084 multiplied by the outlet temperature 22, inlet temperature 14, from which we can calculate the mass flow rate of the water as 32.5 kilograms per second. I've previously mentioned how important it is in heat exchangers, or that the best type of heat exchangers are normally when you've got a phase change. And what this now illustrates are two things. The one is, as I've mentioned before, is your temperature remains constant. If it wasn't a phase change fluid, then this temperature had to do something like that. So your delta T would be lower. Okay, that's the first thing. The other thing is, look at the mass flow rates required for the heat transfer. For this heat transfer of about 1 megawatt, 1087 kilowatts, the mass flow rate of the steam needs only to be 0.45 kilograms per second, while the mass flow rate of the water needs to be 35.5 kilograms per second. Almost 2 orders of magnitude more mass flow rate that you need to remove the heat out of the steam. Okay. Any questions, ladies and gentlemen? Okay, so we are now busy with the LMTD method. And I'm still going to do an example with you, and then after that, if I can finish with this example today, and I think I can, then we're going to do the second method that can be used to solve heat exchanger methods, and that is the effectiveness NTU method. So that I will introduce with the next lecture. However, let's continue with the next example. And this example is a 2 shell pass and a 4 shell pass heat exchanger. So schematically, it looks like this. There's the 2 shells. Inlet there. Okay. And now we've got glycerine. Glycerine, the inlet temperature of 20 degrees Celsius, and that is being heated so that the outlet temperature of the glycerine is 50 degrees Celsius. Okay. Okay, so it is a 2 shell pass and a 4 tube pass heat exchanger. You don't need to remember stuff like this. You can just look in the textbook, in the tables. They would give you graphs typically of what is a 2 shell, a 4 tube pass, etc. So 4 tubes means that you've got 1, 2, 3, and 4. This is just schematically. So here we've got water at 30 degrees Celsius, hot water, and the water exit temperature would be 40 degrees Celsius. So we are lucky in this case, we've got all the inlet and outlet temperatures. What is also given to us is that This tube diameter is 20, and it is a thin tube. A thin tube. The length is 60 meters, total length of the tube on the inside, 60 meters. The heat transfer coefficient on the outside is equal to 25 watts per square meter degree Celsius. I don't have enough room to write it in here. And the heat transfer coefficient on the inside is 160 watts per square meter degree Celsius. What is also given to us is, remember, that is the tube where the heat transfer is going to occur, because we're going to have a fluid in there and we've got fluid on the outside. So that's going to be where the heat transfer occurs, and it is also given to us that there's fouling, and the fouling is equal to 0.006 square meters Kelvin per watt. No value is given of the inside fouling. And the question is to determine the heat transfer rate with the fouling and without the fouling, so that we can see what is the effect of the fouling. Do you all follow the problem? Okay. So just to make it a little bit more clear, there's the glycerine. It goes through this shell here, everything like that. And then at the stage it would go through there. It will be more complicated because there will be more baffles in it. And then it will go through this shell, like there, before going out, like that. Okay. While the water at 80 degrees Celsius is going to be in this tube, flowing like that. Okay. That is the 2 tube passes, 3 tube passes, and 4 tube passes before it goes out. The heat transfer rate occurs on that surface, and the total length of this tube is 60 meters. The heat transfer coefficient on the outside of the tube is 25, on the inside it's 160, and we have to determine the heat transfer rate. Okay. Now, as I've mentioned previously, although this is not a parallel counterflow heat exchanger, we make it as if it is a counterflow heat exchanger. And I just by myself always prefer to start with the hot side. So the hot side inlet temperature is 80. Okay. The hot side outlet temperature is 40. There is 40, 80 and 40, so something like that. Okay. Now we've got to look at the other stream, and we look at what is the inlet temperature. There's the inlet, it's 20. So to make it counterflow, that temperature there must be 20. The outlet flow temperature is 50. There's 50. And now we've got it as if it is a counterflow heat exchanger. The LMTD is equal to 80 minus 50 is 30. Okay, that temperature difference. This temperature difference is 20. So 30 minus 20 divided by the ln of 30 divided by 20. And it gives us an LMTD of 24.7 degrees Celsius. Does it look right? Yes, it should be higher than 20. It should be lower than 30. It looks okay. Okay. The other thing that we have to do, excuse me, when we've got heat exchangers, which is not like a parallel flow or counterflow, is we need to get the correction factor F. Okay, now getting the correction factor F is in figure 11.8b in your textbook. and it is actually this one here below. Do you see it? 2 shell pass and 4 tube pass heat exchanger. And you can see the capital T's is for the shell, and the small t's is for the inner tube. Okay, so it means that that is T1 and that is T2. Do you agree? And that must be capital T1 and that is capital T2, like that. You just need to align your physical problem with the sketch. So, from figure 11.18b, we can calculate the value of P, which is T2 minus T1, divided by capital T1 minus small t1. Small t2 is 40, minus small t1 is 80, divided by capital T1, which is 20, minus small t1 is 80. Okay? And that works out as 0.67. You agree with that? You're all fine with that? Okay, the same with the R. Where do I get the P and the R? It's from the sketch. You don't need to remember it. P and R, T1 minus T2, divided by T2 minus T1, small. Capital T1, excuse me, is 20. Small t2 is 40. T2, small t2 is 40. Minus small t1 is 80. And that is equal to 0.75. So, using these two values of F and R, help me from the sketch. What is the correction factor? We need to look at the bottom one, because that's the 2 shell pass and the 4 tube passes. There's values of R, 0.75. We do not have exactly an 0.75. It's between 0.6 and 0.8. And then the R is 0.75. Yeah, we don't have 0.75 between 0.6 and 0.8. And the P value is at the bottom. And that is 0.67, so about 0.7. So the correction factor is equal to about 0.91. Is it fine? Or did I misread it from the graph? It's about right? Okay. If not, then obviously you can go and refine it at home, but look at the principle of how you get the correction factor. So now that we've got the correction factor, we can start getting the heat transfer rate. We first need to get the overall heat transfer coefficient. The equation for the overall heat transfer coefficient, there it is, 1 divided by U is equal to 1 divided by heat transfer coefficient on the inside, the area on the inside, plus the fouling on the inside divided by the heat multiplied by the area on the inside, plus the ln of the diametral ratio divided by 2 pi KL, plus the fouling on the outside, plus the heat transfer coefficient on the outside. Okay. So let's look at the case for no fouling. If there's no fouling, well, firstly, before we get to the fouling, this area, they said the tube is very thin. Okay. So if it's very thin, and they don't even give the inlet and outlet diameters, then we can say this area would cancel out. Again, this is thin, so the lim of those two diameters would be 1, it's 0. So that term is negligible. Okay. If there's no fouling, then obviously this term also disappears. So it means that 1 divided by U can be written as 1 divided by the heat transfer coefficient on the inside plus 1 divided by the heat transfer coefficient on the outside. The heat transfer coefficient on the inside is 1060. The heat transfer coefficient on the outside is equal to 25. And if we solve it, then we get the overall heat transfer coefficient is 21.6 watts per square meter Kelvin. Okay, so getting to the heat transfer rate, we can now say the heat transfer rate is equal to U multiplied by the area, multiplied by the correction factor, multiplied by the LMTD, as if it is a counterflow heat exchanger. It is not. We make it a counterflow heat exchanger, but then we need to get the correction factor F. Okay, the overall heat transfer coefficient is 21.6. The surface area is pi multiplied by the diameter of the tube. 20 millimeters, there it is. Multiplied by the length, which is 60. That is the surface area. Multiplied by the correction factor, which is equal to 0.91. Multiplied by the LMTD, and the LMTD is 24.7. And the result is a heat transfer rate of 1,830 watts. A small heat exchanger. Do you get the idea? Okay. So when doing this, we've looked at this resistance term, and we've said that firstly, no fouling, so we didn't add this term. Now we need to redo it, but we need to add that term. So again, with fouling, we're going to have the equation 1 divided by U is equal to 1 divided by the heat transfer coefficient on the inside. Fouling was on the outside, plus 1 divided by the heat transfer coefficient on the outside, plus the fouling on the outside. Remember, the area cancelled out because the inlet area and the outlet area is exactly the same. It is a thin-walled tube. Okay, now in this case, the overall heat transfer coefficient is going to decrease. It cannot increase. Okay. If it increases, it will enhance the heat transfer, so it needs to decrease. So you can see it is not significant. Maybe the fouling just started, and you can go and redo the calculation. UAF multiplied by LMTD, as if it's a counterflow. The heat transfer rate is equal to U, which is now 21.3. The surface area for heat transfer is pi multiplied by the tube diameter, which is 20, multiplied by the tube length, which is 60, multiplied by LMTD, and the LMTD is equal to 24.7. and that gives us a heat transfer rate of not much less than that. And the reason is the overall heat transfer coefficient didn't change that much. Do you follow? Any questions, ladies and gentlemen? If not, then thank you very much. And then tomorrow, or the next lecture, we will continue with the effectiveness NTU method. Thank you very much.